Have you ever thought about how math can tell a story? It sounds a little weird, right? But that's exactly what we're going to do today. We're taking a journey into the world of functions. And really, you can just think of them as these different families of shapes, and each one has its own special way of describing something happening in the real world. So, let's start with something super simple. How could math possibly describe something like just going for a run in the park? Well, it all comes down to finding a connection, a relationship between two things. In this case, it's pretty obvious: how far you've gone and how long it's taken you to get there.
All right, let's take a look. Here we have a graph of Jessica's 9-mile run. You can see along the bottom we've got time measured in minutes, and going up the side is the distance she's covered in miles. Now the key thing here is that she's running at a really steady, constant pace. And because of that, when you plot the relationship between her time and her distance, you get this perfect straight line.
And that straight line, that's our starting point. It's our first and honestly most fundamental type of function. It tells the absolute simplest story you can imagine, the story of something changing at a constant, steady rate. So this has a name, of course. It's called a linear function. And any function that makes a straight line is going to follow this basic recipe: f of x equals ax plus b. Now, don't get hung up on the letters. That a and that b are just numbers. They're like the control knobs that tell you how steep the line is and exactly where it sits on the graph. And that steepness, it's got a special name: the slope. And honestly, the slope is the absolute key to understanding a linear function. It's not just a number. It is the rate of change. So, if we go back to Jessica's run, the slope of her line is literally her speed. It's the exact number of miles she runs every single minute. Okay, so check this out. The number you get for the slope actually tells you a lot. See that red line? It has a positive slope, so it's going up. The green one has a negative slope, so it's heading down. And what if the slope is 0? Well, you get a totally flat, horizontal line. And how do we find that number? It's that classic rise over run calculation, just the vertical change divided by the horizontal change between any 2 points on the line.
Right, so straight lines are great, but life isn't always a straight line, is it? What happens when the story has a twist? What if things speed up or slow down? Well, that's when our nice, simple straight lines have to start to curve.
So for these more complicated stories, the ones with twists and turns and peaks and valleys, we need to upgrade our toolkit. We need something more powerful. And that's where this next family of functions comes in. They're called polynomials. So what are polynomials? Basically, they're just built by adding together bits where our variable, x, is raised to a power. Like x squared or x cubed, and so on. And here's a fun fact: our simple little linear function, it's actually the most basic polynomial of all. It's just one where the highest power of x is, well, 1. And that power that you raise x to, it has a huge impact on what the graph looks like. If you use an even power, like x squared or x to the 4th, you get these awesome, perfectly symmetrical U shapes. But if you use an odd power like x cubed, you get these cool, kind of rotating S curves. And this is where you really see how powerful these things are. I mean, a simple x squared function, we call that a quadratic, can perfectly map out the arc of a ball you throw in the air. That U shape is called a parabola. And the more complex ones, man, they can model everything from the twists and turns of a roller coaster to the wild ups and downs of the stock market. Okay, so we've got lines and we've got curves from polynomials. Let's kind of zoom out for a second and see where these guys fit into the bigger picture. Turns out there are really two main superfamilies of functions. On one side, you've got what are called algebraic functions. These are pretty much what they sound like. They're built using all the basic tools of algebra that we already know: adding, subtracting, multiplying, dividing, taking roots. Then on the other side, you have transcendental functions. These guys kind of go beyond basic algebra. They're for describing things like explosive exponential growth using logarithms or the rhythm of natural cycles with those wave-like sine functions.
So, the polynomials we've been talking about, they fit right into that algebraic family. But they've got some cousins too. You've got rational functions, which are basically just fractions where the top and bottom are both polynomials, and you've got root functions, like your classic square root. They're all part of this big extended family, all built from the same fundamental building blocks.
All right, so think about this. Every function we've seen so far has followed one single rule for its entire existence. But what if the rules could change partway through the game? For that, we need a special kind of function, one that kind of has multiple personalities. And that's exactly what it's called, a piecewise-defined function. The name says it all, right? It's one single function, but it's defined in different pieces.
It follows one formula for a while and then, bam, it switches to a completely different one.
And you might think this sounds weirdly abstract, but these things are everywhere in the real world. Just look at this graph of parking fees. It's a perfect example. The price is flat for the first hour, right? But the second you go 1 minute over, the price jumps up to a new level. Then it stays flat again for a while and then jumps again. That step pattern, that's a piecewise function in action.
So, we've got these basic families, lines, polynomials, and a few others. But here's the really cool part, the big secret. The real power isn't about memorizing a million different function types. It's about learning just a few simple rules to tweak and modify the basic ones. This is your mathematical toolkit.
For example, we can take a basic shape, like our friend the parabola here, and just by adding or subtracting a number at the end, we can literally slide the whole thing straight up or down. The shape doesn't change at all, it just moves.
And guess what? We can do the exact same thing sideways if we add or subtract a number right inside the function, next to the x. We can slide the whole graph left or right.
And one more thing. If we multiply the whole function by a number, we can stretch it out vertically, making it taller and skinnier, or squash it down, making it shorter and wider. All these little tweaks, shifting, sliding, stretching, they have a name. They're called transformations.
And this is the whole point. This is the big idea. We don't need an infinite list of functions to memorize. All we need are a few basic parent shapes. By using these simple transformations, shifting them, stretching them, flipping them, we can basically create a custom function to describe almost any pattern you can possibly imagine.
So I'm going to leave you with this thought. Just look around you for the rest of the day. Look at the arc of a water fountain, or how a plant grows towards the sun, or even something as boring as how your phone bill works. What pattern out there, in your world, do you think you could now describe with a function?